Hey everyone, and welcome to our first lesson in Unit 6. Today's lesson is going to be on the periodic table, and it's actually going to be split into two lessons because we do cover a fair amount within this topic. Today's lesson is going to be an introduction into the periodic table, and by the end of the lesson you should be able to identify and describe periodic trends on the periodic table and be able to describe atomic radius, electronegativity, and ionization energy. Now, the development of the periodic table, it was originally developed in 1869 by a gentleman named Dmitri Mendeleev and Lothar Meyer. And really it is, from what they initially developed, and we'll see this here in a moment, it's kind of changed and developed over time into what we know of as the modern periodic table, which abides by modern periodic law, basically stating that properties of elements are periodic functions of their atomic numbers, so the number of protons in their nucleus. And this means that as the trend of atomic number increases, there's going to be certain properties that are going to repeat at certain and specific intervals, otherwise known as periods, how we get the periodic table. Now I'm going to show you a little video on the development of the periodic table.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitri Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, "Y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behave. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time. Scandium, germanium, rhenium. The element he called Eka manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907. but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
Now we can see from that video that Mendeleev was able to predict properties of unknown elements based off of these repeating patterns that he was noticing. And although his table was organized by the atomic mass of elements, it is now organized by the atomic number, which also increases because we're increasing the number of particles in our nucleus, therefore by increasing the overall mass of the atom. Now we know that the table is split into columns and rows, and the columns are going to be called groups and the rows are going to be called periods. And if we look at each row or column, there's going to be different patterns and trends that we're going to see amongst the elements. And this is really the unique part of the periodic table and why it is set up the way it is. And we'll talk about different parts here and why they're set up the way they are. The periods of the periodic table are going to be the rows that run from left to right. And we've talked a little bit about this, but all the elements that are in the same period have the same number of principal energy levels. For example, we consider the elements in period 3, sodium, magnesium, aluminum, silicon, phosphorus, chlorine, and argon all have 3 principal energy levels. And if we look at their electron configuration, they would contain 3 numbers apiece. Now the groups are going to run from top to bottom or up and down, and elements that are in the same group have the same number of valence electrons. So if we look at the electron configuration of all the elements in the same group, they're all going to have the same number of valence electrons, the same number at the end of their electron configuration. And as a result of this, valence electrons are going to determine reactivity of an element or of an atom, and therefore elements that are in the same group are going to have similar chemical properties because they have the same number of valence electrons and therefore are looking with a similar desire to try and bond with other atoms. Now, for example, in group 1 we have lithium, sodium, potassium, rubidium, cesium, francium, and they all like to lose 1 electron to obtain their full valence shell, and therefore they all like to form +1 ions, and they are all extremely reactive. As far as sizes of atoms, we're going to measure that and call that atomic radius, and this is actually measured kind of almost with a diameter and taking half of that distance. But if we were to take 2 atoms of an element in the solid phase and measure the distance between 2 nuclei, we're going to take half that distance and we're going to call it the atomic radius of that atom. Now within a period, so going from left to right, the radius is generally going to decrease as atomic number increases, which means the radius decreases as you go left to right. And this is because that as we go from left to right, we have more protons in our nucleus. The atomic number is increasing. So the attractive forces between the protons in the nucleus and the valence electrons becomes stronger, and it pulls those outer valence electrons closer in towards the nucleus, therefore making the actual radius of the atom smaller. And this is as we go left to right. Within the group, going from top to bottom, radius is generally going to increase as atomic number increases. And this is because as we go down the group, we go down 1 additional period, which means we have 1 additional principal energy level, and PELs take up more space. And we can see this with the graphic here, the 2 different trends. Atomic radius decreasing from left to right, no matter which period we're in, and increasing down the group from top to bottom. So our largest atoms are in the bottom left of the periodic table, and the smallest atoms are in the upper right. And what's nice about the periodic table and the way it's set up, we will notice a lot of different trends, and this helps us to predict different properties of different elements. Now the periodic table itself is divided into three really main subgroups, which we'll call metals, metalloids, or you sometimes see that called semimetals, and nonmetals. And looking on the table, we can see really two different variations, or really I guess a gray and a white and a darker gray. And hydrogen's kind of hiding up here, but this is in the white group as well, so we're going to call that generally as a non-metal, although it can behave as a metal depending on what it's bonding with, but we'll treat it as a non-metal. The metals are this light gray area over on the left side here, and what separates our non-metals from our metals are going to be our semi-metals. It's kind of like a blurred line between the two, and that's going to be these dark gray elements running here. And if we look closely at it, there's actually a little staircase that runs through here, and that's what's going to separate our metals and our nonmetals. Metals being to the left of the staircase, nonmetals being to the right, and metalloids pretty much lining up on or below the staircase itself. And that is emphasized in your reference table as well with a bolded line. And depending where these elements are on the table, it's going to help determine properties and what they're going to want to bond and react with. You know, electronegativity, we know, is an atom's attraction for electrons when involved in a chemical bond. And elements that have a smaller radius tend to have a greater attraction and a higher electronegativity. Now, since this is related to size, our higher or more electronegative elements are going to be in the upper right of the corner. We see this trend in increasing electronegativity from the lower left of the table up to the upper right, which basically goes along with the size of our elements, or of our atoms. Now we know as far as electronegativity, fluorine was set as the highest value, but all the other values for electronegativity are listed on table S. Now metallic character is exactly what it sounds like, how a particular element is more metallic. We know metals are on the left side of a staircase as well as in the middle of the periodic table, and metals are going to tend to lose electrons and form cations. And elements that have a low electronegativity and like to lose electrons easily have high metallic character, and those are going to be most of our, really all of our metallic elements, kind of depending on what they're going to be bonding with. Non-metallic character is going to be the opposite, so it's going to describe the non-metals on the right side of the staircase on the table, and non-metals like to gain electrons and form anions. So if an element has a high electronegativity and likes to gain electrons, we say that it has high non-metallic character. So we have high non-metallic character in the upper right and high metallic character in the lower left of our periodic table. Now, first ionization energy, we know, is the energy required to remove the most loosely held valence electron from an atom. The outermost loosely held valence electron that's going to be easiest to take away. The first ionization energy is going to describe how much energy is required to actually take it away from the atom itself. And this is directly proportional to electronegativity, because the more tightly that atom is attracted to its electrons, the more energy it's going to take to remove that electron. Now, looking at some of the properties of our three subgroups, metals, we know, as we just described, have low electronegativity, low ionization energy, and a large atomic radius. They like to lose electrons and form cations, or positive ions. Metals, and some of this might seem kind of intuitive as far as your knowledge of metal itself, but metals are excellent conductors of heat and electricity. Two vocabulary words that you have to make sure that you know are malleable and ductile. Malleable means that you can take a metal and hammer it, and it's not going to break apart into pieces. It's going to kind of get bent and misshapen and deformed. And metals are also ductile, meaning that they can be drawn or pulled into a wire. In general, metals are going to have luster. They're going to have a shine to them. And metals make up a little more than 2/3 of all the elements. And as we had just talked about, metallic character increases as ionization energy decreases. Now looking at our nonmetals to the right of the staircase, nonmetals are going to have high electronegativity, high ionization energy, a small atomic radius, and they're going to like to gain electrons and form anions or negative ions. Since they are the opposite of metals, they are poor conductors of heat and electricity. You can kind of see the trends there as well. If we were to try and hammer a nonmetal, they are brittle, which means they're going to shatter into pieces when we try to hit them with the hammer. They do not have luster. They're not going to have a shine to them. They're considered dull. And we are going to include hydrogen here. It's kind of thrown in on the top just to kind of see it all together here in the graphic. It's not actually included in group 7. Our metalloids, and sometimes these are, you're going to see these change a little bit depending on what table you're looking at. And you can see kind of with the key there that some are commonly included, some are less commonly included. Some are rarely included. We see that with carbon and aluminum, even though they're kind of close or even have a corner touching the staircase. But metalloids are going to fall in between with properties between metals and nonmetals. So metalloids or semimetals are going to have medium electronegativity, medium ionization energy, medium radius. They'll share electrons. They'll form positive and negative ions. It's going to depend what they're bonding with. They fall in between as far as conductors, so they're semiconductors of heat and electricity. That's why we use them for making microchips. Those are properties that can be turned on and off, essentially. They do have luster like metals, but they're brittle like nonmetals. So if we try to hit them with a hammer, they're going to likely shatter into smaller pieces. And again, these are going to be the elements that are above and below the staircase, generally excluding aluminum and carbon. Now moving on to ions, for every electron that an atom gains, it's going to become more negatively charged. If we gain extra negative particles without gaining positive particles to balance them, then we're going to have an excess of negative charge. So if we gain 3 electrons, we become a -3 ion. Or if we lose 2 electrons, we're not going to gain extra negative charge, but we're going to have an imbalance of positive to negative, so we're going to become a +2 ion. Remember, depending if we gain or lose, however many electrons that is, we become a minus or positive ion, depending on how many electrons were lost or gained. Now, an atom becomes an ion. It's trying to gain or lose electrons, so it can end up with that stable octet, a full valence shell of 8 electrons. Now in general, when an atom has 1 to 3 valence electrons, they usually get lost and become a cation. For example, sodium in group 1 likes to lose that outer 1 electron and become a +1 sodium ion and have a noble gas configuration of 2,8. Generally, if atoms have 5 to 7 valence electrons, they will try and gain electrons to become an anion to fill their valence shell. For example, chlorine, with its configuration of 287, likes to gain 1 electron to fill its valence shell and have a stable octet, which would make it a -1 ion. Now, ionic radius is different than atomic radius. So ionic radius, depending if we gain or lose electrons, it's going to affect how large the atom is. So the ionic radius is going to be different than the atomic radius. Now when metal atoms lose an electron, they're trying to get to their full valence shell, but they generally lose the entire outer principal energy level, so they become much smaller. So we looked at sodium on the last slide. When sodium loses its outer 1 electron, it loses the whole 3rd principal energy level, and its ion only has 2 principal energy levels with electrons in it. There's no electron in a PEL. The PEL is essentially gone. Now, metal ions have a smaller radius than metal atoms, and that's a trend that is consistent and something that you want to make sure that you remember. And since it is the periodic table and very trendy, it is going to be true in the opposite sense for anions. So when non-metal atoms gain electrons, they add an electron or more to make a stable octet, which increases, since we have extra electric particles or electrically charged particles in our electron cloud without offsetting positive charges in our nucleus, we get this electron repulsion between these extra electrons in our valence shell. That repulsion causes the cloud to become a little bit larger, and we saw this in the simulator a few lessons back. Now, in general, nonmetal ions are going to have a larger radius than nonmetal atoms, and that's a trend that, again, you'll want to make sure that you remember, which is the opposite for metal ions. So metal ions are going to get smaller, and nonmetal ions are going to get larger. Now, this example here of the periodic table, and you can see these in a variety of different ways, show all the different groups that we have, which we'll get into in a later lesson here. But we can see different groups, and they're all color coded, group 18 being noble gases. And some of these indicated based on their properties as far as being poor metals. So we're going to look at, these aren't really split up between semi-metals really well. Some indicated by the phase of matter that they're in. And we can see on the bottom here we have two groups, lanthanoids and actinoids, that are kind of separated from our table. And one, if we were to put these two rows in here, this would make this much larger and would leave a void because we don't have the same corresponding rows further up here. So this would look a lot different and leave a gap. But also, this has to do with how electrons are filling in the electron cloud and in the principal energy levels. And this group down here fills a certain sublevel differently compared to other groups further up on the table. And that's one of the main reasons why it's separated down on the bottom. We'll get into more of the periodic table in our next lesson. If you have any questions, make sure you come see me. Have a great day.